Today we're going to talk more about right triangles, and we're going to talk specifically about a special type of right triangle we call isosceles right triangles. So it's first important to bring up, what does it mean to be an isosceles triangle? You might already know that. It's something you've definitely heard before, but we haven't really talked about too much this year. And an isosceles triangle is a triangle that has two sides that are congruent, so the same size, same length, and therefore two angles that are congruent, that are the same measure, and those angles are across from the sides that are congruent. So in this picture on the left, I have an isosceles triangle. These two sides are congruent, as indicated by the little hash marks. And so then those angles across from those sides are also congruent. They're the same size. So an isosceles right triangle is a special kind of right triangle. It's a right triangle that has two 45-degree angles, two congruent angles. And so therefore the sides across from those 45-degree angles are the same length. So the two legs in this triangle, so the legs in this triangle are both the same length. So we know a special relationship that exists between the two legs, the two congruent legs in a isosceles right triangle, and its hypotenuse. So let's assume that one of these legs is 1 unit long. We know, after what we just saw on the last slide, that the other leg should be the same length, 1 unit long. And in the last lesson, we talked about Pythagorean Theorem. If you know two sides, the lengths of two sides in a right triangle, then you can find the third side. So we can use Pythagorean Theorem to figure out how long this hypotenuse should be. We'll plug 1 in for A and B. Simplify. Sorry about that. So 1 squared and 1 squared are both 1. Add them together, square root both sides, and we'll find out that the hypotenuse in this right triangle is the square root of 2. This isosceles right triangle with side lengths, or leg lengths 1 and hypotenuse square root of 2 is something we call a reference triangle. We can use this reference triangle to figure out the lengths of sides in isosceles right triangles if they're different from 1 and square root of 2. So let's use this reference triangle to try and solve some isosceles right triangles. So here I have an isosceles right triangle. It's got one 45-degree angle, and so that means that the other angle there is also 45 degrees. I know how long one side is, but I don't know how long the other two are. So if I knew two of the sides, I could just use Pythagorean Theorem. But I only know one of the sides, so now I can use the reference triangle to write some fractions, to write some proportions, to figure out what the hypotenuse is and this other side here. So I do that by dividing the hypotenuse by the square root of 2 from our reference triangle, and I divide both legs by 1. Our reference triangle had legs that were 1, and a hypotenuse that's the square root of 2. They're similar triangles because all the angles are the same. And we know that in two triangles that have two congruent pairs of angles are similar, and we can write these proportions. So that's what we're going to do with these fractions. I'm going to take my fraction with x in it, and then my fraction 8 over 1, the one that doesn't have a variable in it, I'm going to set them equal to each other. And I can cross multiply 1 times x and 8 times root 2. And I find out that x is equal to 8 root 2. So I can't actually multiply the 8 and the root 2 without getting some sort of decimal. And so we just write them next to each other as 8 root 2. Both legs in an isosceles right triangle should be equal, so we should know straight away that y is equal to 8. But in case we don't realize that, it's okay. We can write a proportion. Oops. We can write a proportion that says y over 1 equals 8 over 1 and figure out that y equals 8. Again, remember, we're allowed to write these proportions because this triangle here is similar to our reference triangle because they have congruent angles. So let's try another one. Again, I have a isosceles right triangle, 45-degree angle. A lot of times they only show one of them, and you'll know that the other one is 45. The two legs, I'm going to divide by 1. And the hypotenuse, I'm going to divide by 2. That's using our reference triangle to create fractions that we can use to write proportions. Both legs should end up being equal to the same thing because they're supposed to be the same. So my two proportions look like that. I really only need to solve one of them. We have to do something a little tricky here. Whenever we have division by a square root, we don't like that. So we have to clean that up a bit. And anytime we're dividing by 1, we can kind of get rid of the divided by 1 because dividing by anything by 1 leaves it as itself. So x divided by 1 is x, y divided by 1 is y. And so the only thing we have to do to clean up these two answers is what we call rationalize the denominator. It sounds complicated. It's really not. We just have to multiply the top and the bottom of this fraction by this square root. So I'm going to multiply the top and the bottom both by the square root of 2. And so the top 6 times square root of 2 just looks like that. These two square roots, we can multiply them since they're both square roots and get the square root of 4. We know the square root of 4 is 2. And then we can just simplify that 6 and that 2 to be 3. So this 6 divided by root 2 simplifies to be 3 root 2. And since x and y are both the legs, they're both the same length, both x and y are equal to 3 root 2. Now, I don't expect you to be a pro at rationalizing denominators after that one example. So please, if that was difficult for you, make sure you ask me about it in class and I can show it again and you can ask some more questions. So I want to do one last one with you. The process is still the same. I have an isosceles right triangle. I know that because I have one 45-degree angle, which means the other one is also 45. I divide both of the legs by 1 and the hypotenuse by the square root of 2. At this point, the dividing by 1 becomes just extra work, kind of. It's good to show it here, but we should figure out that when you divide something by 1, that divided by 1 kind of goes away. And so we can end up writing m over root 2 equals 3 root 3 over 2. So that divided by 1, that makes this look very complicated, can just go away. And then n over 1, we don't really even need the over 1 anymore. So straight away we know that n is the same as this other leg. The two legs should be the same. So we just have to solve this one for m. I'm going to cross multiply 2 times m and 3 root 3 times root 2. I'm allowed to multiply the root 2 and the root 3 together since they're both underneath square roots. That gives me root 6. And then I need to divide both sides by 2. And I get this as my final answer for m. It looks complicated, but that's the answer. So again, just a real quick wrap up. We're using reference triangles for isosceles right triangles to write fractions. Our reference triangle is always going to be similar to any other isosceles right triangle because they have congruent angles. And so we can take those fractions to write proportions like we did in similar triangles and find the missing pieces. I will say this as a side note. If you find one of these values, x or y, you can always use the Pythagorean theorem to find the other one. So when in doubt, if you find one and you don't know how to get to the other one, you can always use Pythagorean theorem. Give this one problem a try. find the length of the hypotenuse and the length of y here, the other leg. If you have questions, make sure you're ready to ask them in class.